Welcome to the course on two-dimensional signal processing, principles and practices. We had completed the signal plotting and the operations on signal for 1D and 2D sequences, that is especially discrete sequences. And what we are going to handle throughout this course in this signal processing. Coming to the sampling, so today we will understand that what is sampling and what are the insights of it, what is to be done, known about the sampling, so that can be extended to 2D as well. So taking a signal x of t, which is varying with respect to t, you can see the independent variable t and x of t which is plotted. To sample it, we have to multiply this function with the impulse train. So the impulse train del of t, unit impulse train, when the amplitude is 1 and its time period is t, so which is varying in this fashion. So here this impulse, now we multiply this 2, that is nothing but the sampling operation, or modulating this signal with impulse. So we get the multiplication as this impulse. Now the amplitude is now changed because of this multiplication. It's not unity anymore, and this value of signal x of t would be obtained here. So this is similar to the impulse amplitude would be similar to the value what is given over here. So this is x of delta t, so because this is a multiplied one. So in the sampling operation we get this sample, these samples from the signal. In between values are not defined, and that is depending on the sampling time we use. This is the period t for which this is multiplied here. So this is available only at t, 2t, 3t and so on, and in between this impulse is not defined. So the sampled sequence what we get is this. So when we do the sampling, what are the points needs to be noted. So this is a continuous in time signal whose spectrum is band limited. That means sampling theorem assumes that this band limited signal for which the x of omega is equal to 0 for omega greater than 2 pi b. B is the bandwidth. It is not defined, x of omega is not defined more than b hertz, that is the bandwidth. So this signal should have a bandwidth, and it can be sampled using at least with a sampling frequency fs should be greater than or equal to 2b samples per second, so that from the sampled sequence we can get back the analog signal, or reconstruction is possible only when we follow this Nyquist sampling theorem. And the signal to be considered, the maths behind this is x of t. Okay, so when we do the sampling, what we do, x of t into del of t, what we have done, this has a period t, capital T, that is periodic sequence, and that are impulse train and unit amplitude. So we get, what we get is x delta of t, and which can be visualized as x of n t del of t minus nt. So this is the sequence now. Any arbitrary sequence can be written in terms of sum of shifted impulses and its amplitude, right? So this is what we get after the sampling. So this x of t is periodic, one thing to be noted, and to get the spectrum of this sequence or every sequence, what should be done. So x of t, what is the spectrum, and del of t, what is the spectrum, and what is the spectrum of x del of t. So this we would see. First, writing this del of t in trigonometric series, because it is a periodic sequence. So we use the Fourier series. So trigonometric Fourier series, if we express it, that 1 by t into 1 plus 2 cos omega st. So that impulse train would be plus 2 cos 2 omega st plus 2 cos 3 omega st and so on. So it would have all the frequencies here, and the time period is 1 by t. So if we take this is del of t, and what is omega s is 2 pi by t, that is related to the sampling frequency or the time period t used for the impulse train. So now x delta of t from this, so multiply this x of t with delta of t. So then del of t is going to be, now in this case here is replaced, we have this 1 replaced with x of t, and this is multiplied with x of t, here x of t everything. So 1 by t x of t, 2 into x of t. So you see the change in the amplitude of this the multiplication you can observe here in the x of del t. So this is the sequence which we get after writing it in terms of the trigonometric Fourier series delta t and multiplication of x and delta. So from now getting the spectrum or the Fourier transform of the signal, because the signal which we had taken x of t is aperiodic, which is not periodic, and it is continuous. So when it maps into the frequency domain, that is, this is also aperiodic and it is continuous. So aperiodicity maps into continuous and continuous maps into aperiodicity. So that's why this get this x omega, you get the band limited spectrum B and minus B, and its amplitude is something A depends on the signal which is taken in the continuous time domain. So now what is the frequency domain representation of the del of t? That is del of omega. If we take that, this is going to be 2 pi by t, and we have plotted with f. You can note that this x-axis is frequency omega by 2 pi, and at every fs this would repeat, right? The same thing as an impulse what we get at t and 2t, then now this is going to be fs, 2fs, 3fs and so on. Similarly here minus fs, minus 2fs and so on. So this is del of omega. So when multiplication in the time domain of x of t into del of t, and the resultant one be the convolution of that these two in the frequency domain. So or if you take the spectrum of this x of del of t, then the spectrum would look like this. That means this is going to be the pattern of baseband is going to be repeated. So b to minus b, and this is with respect to fs, and here it is 2fs. So similarly that would continue from minus infinity to plus infinity. The discretization process or the case of having the sampling, the signal now has become discrete, and so the discrete one is representing here the periodicity. Okay, so the periodicity comes from the discrete nature of the sequence which is sampled. So this particular pattern of band limited thing is getting repeated with respect to fs, 2fs in this case in the Fourier domain. So if you just sample it, the sequence, the convolution of these two gives x of del of omega, or separately this sample which we had taken over here. So this multiplying this and getting the x delta of t, and take the Fourier transform. This is discrete signal and it is aperiodic. Okay, so the aperiodicity maps into continuous, but discrete maps into periodic. That's why we get the spectrum in this case. Second one, you have this continuous spectrum, but it is periodic. So now how can we express in that? So x delta of t, x of t delta of t multiplied. So we have this equation now. So after multiplication in the time domain, so can we simplify this further? So x of t cos omega st, so whose Fourier transform if we take 1 by 2 x of omega plus omega s plus x of omega minus omega s. So this is x of t whose Fourier transform is x of omega. If you multiply by cos of omega t, so this would omega plus what is the omega which is this frequency contains, and you can have the two spikes in the spectrum, one at omega s plus omega s and another one at minus omega s. So applying this in this equation, so this equation 1 by t x of omega, and this would be now changing to x omega minus omega s. So this 2 gets cancelled, and similarly omega minus 2 omega s, omega plus 2 omega s and so on. So this would have the values, and in this case 2 x of t cos 3 omega m s, similarly x of omega minus 3 omega s plus x of omega plus 3 omega s you would have. So summing up together, x delta of omega 1 by t x of omega minus n omega s, where n is varying from minus infinity to plus infinity. So you will have this at 0, 1 and then 2, 3 and so on. Similarly at the negative indices as well, plus omega and then plus 2 omega and plus 3 omega and so on. So this is the expression of the spectrum what we got after the sampling. So now the sampled sequence with the, can it be reconstructed? That's what, if you follow the Shannon's sampling theorem, yes, this could be reconstructed, that x of t can be obtained actually. So if this is x of t and its spectrum is x of omega. We got this spectrum, and impulse when it x of t passes through del of t, otherwise multiply it, and we got this sequence, that is a sampled sequence, and whose spectrum is a repeated x of omega. This pattern is repeated because of discrete one, and continuous nature has come from the aperiodicity. And after getting this one, pass it through the low pass filter, just to similarly here. So if you look at this dotted lines, this is the low pass filter, the ideal low pass filter, but in reality this won't be an ideal low pass filter. It will have a slope of transition width, and then there is a ripple and so on. So if you pass it through this filter and then remove all these components which were there repeated here, replicas at fs, we have 2fs and up to infinity and minus infinity, and get back this one alone in the frequency domain. So you can see that a by t, and by clipping off all other frequencies, we get only the base frequency. That means this spectrum is equivalent to this spectrum. If you are able to get it in the frequency domain, the same thing is possible in the case of time domain as well. So it can be visualized here. So that is a low pass filter which is passed out. This is passed here, filtered with the low pass filter, and we get the sequence here x of t as such, and then this is the one which we got. So these two are, we call it as reconstructed, as which the process of getting it is different. So this x hat of t and x hat of omega represent the reconstructed signals. It's possible, if you follow the Shannon sampling theorem, then it is possible to get it back. So for that, what we need to sampling frequency, which needs to be chopping the sequence, collecting the data at a rate fs at least 2b. B is the bandwidth of the sequence. So minimum sampling rate should be this for x of t to reconstruct it from its samples. So let's take an example. Suppose this is x of t, whose sequence is this x of t equal to sinc square phi pi t. This can be a sinc function which is multiplied twice, that is sinc square, so that the magnitude is, you can see the positive values here, and 0.2, this is at 0 minus 0.20, so it is going in this fashion. So x of t is this signal, and whose Fourier transform, if you take x of omega, so 0, which is given phi to minus phi. This is to just understand the sampling concept. So we will deal the Fourier transform details little later. Right now, it is for sinc, it is going to be a triangular function. So that's known for the Fourier transform pairs. From that we took for rectangular function, it's a sinc function. So sinc function, it should be a rectangular function. So these are Fourier transform pairs. The f this is plotted with f, and this is x of omega. So if we have this xt and its function x of omega is 0.2, the triangle function is defined like this. Omega by the base is maximum 20 pi. So this is 2 pi f, that going to be 10 pi, and here minus 10 pi. So what this is, the base is totally 20 pi, that's what is represented, and the amplitude is given as 0.2. So this comes from here where it crosses this 1 by t. So x of omega is this, and for the given xt, this is x of omega. Just let us take this Fourier transform, and how to obtain this we will see that later. Just to understand the sampling concept, we had taken this example. So from this f, the bandwidth is here, b is 5 hertz, or 2 pi 5, which is equal to 10 pi. So what's the sampling frequency required? The fs should be at least 2 times this 5 hertz, that is 10. So it should be, fs should be at least 10 to get the signal back, or the reconstruction is possible. So if you learn the thing, which is, for suppose sampling frequency is 5, so but we need is 10, at least 10. So this is called the undersampling. So we just take one, this frequency is sampled at a rate of 5 hertz. Okay, so if the one sample and only the case few samples have been taken, it is not even followed the Shannon sampling theorem. So what is t here is 1 by 5, which is 0.2, and x of omega, what happens, this x of omega 0.2 into this omega by 20 pi. So 0.2 into 1 by t, that is 0.2, this becomes 1. So this is the x of del omega. So where x of omega was this. Okay, so here, so what we get is, you can see the base of that, the triangular function 5 and minus 5. This gets overlapped This would be next one would be at Fs, right? So because of the repetition we have seen, when you use the sampling, the resultant spectrum would follow have the repetition of this baseband, which is this at Fs, and then another at 2 Fs, that is at 10, and another at 3 Fs, that is going to be 15, and next at 4 Fs, 5 Fs, and so on. Similarly, the negative side also, minus 5, minus Fs, minus 10, minus 2 Fs, and so on. So this is getting repeated, but if the width is same, right? So this is from plus 5 to minus 5, and here it is 5, this is going to be 0 to 10. So there is a overlap in this area. So which has come from the base frequency or the second spectrum. So ultimately what we are going to do is, we will be using a low pass filter to remove the replicas and get the base spectrum only. So in that case, if you try to remove this signal, so you would not be able to perfectly remove it, because you will have this one, the components here would overlap here, though the high frequency component here also similar to this would appear. So this is called the aliasing. So we'll deal the aliasing concept. So now we could not recover it, the signal back, because these components are from the second Fs component. So if you take the case of Nyquist sampling, at least we had this Fs should be 10. So this is called Nyquist sampling. So T is from here 1 by T 0.1. So 0.2 by 0.1 here. So get there is a change in this, but this was x of omega. Now x del of omega has become 2 into del of this. So take the spectrum of it. You can see this is 2 here instead of 0.2 in the previous case. So Nyquist sampling results this amplitude change here, but you can see that this is going to be 0 to 5, 5 to minus 5, and then next would be at the Fs center, next sample. Fs is now 10, and the base would be plus 5 and minus 5 here. So and next is here 2 Fs, and you can see now this is minus Fs and minus 2 Fs. So if you put it through the low pass filter, so we can easily get this base from 5 to minus 5 to plus 5 directly, and removing all other components which are present in the x del of omega. So the reconstruction is possible in the case of Nyquist sampling theorem Fs. You can see the samples little more compared to the previous case. You have the samples, right number of samples, but if we use the sampling more than that, 10, that is 20, that is called over sampling. So we are sampling it more samples we are taking, and the T is here as of course the between the two samples. So the T equal to 1 by Fs 0.05, and this magnitude has become 4. Let's see this x of del of omega, which is now 0, which has the base of 5 to minus 5, x of omega, that doesn't change, and the next component of this would be centered at Fs, right. So Fs is now 20. It is far away from that, so there is no component in between here. So this is also minus Fs. So now if you put the low pass filter, so this can be recovered easily. So these components can be removed through the filtering process. So undersampling is the only case where the overlapping occurs between the base component and the replication of this Fs and 2 Fs. And but Nyquist sampling and oversampling is the signal can be recovered or the reconstructed, okay, by filtering the process. So through this, just to illustrate that, in case of actually when we sample it, the impulse which had taken in ideal case, it won't be ideal like that. So it would be like there is a small spike and there is a small width in it, and the impulse would look like that. So the impulse has some base values, and then it's not so sharp like in practical cases. So the signal when it is sampled with that impulse would be like this. There will be an amplitude change. Actually, this won't be the spectrum of it will be equal amplitude like in the ideal case. So there will be a change in that was affecting the amplitude of this. So that's just to be known, the amplitude of the base and the repeated spectrum here needs to be known, which is that it is affecting the amplitude. So it can be recovered from its sample very well in that case. So a little bit about the reconstruction process. We would see how the signal is reconstructed. When we pass through the low pass filter, right? So to get back the x of t. So this reconstruction, what are the ways in which we can do it? So first is the case of the zero order hold. So if we take the zero order hold and whose impulse response is given as rectangular of t by t. So it's a rectangular function is t and h of t. It's a continuous time function, and whose width is 0, that is minus t by 2 to plus t by 2, it is t. The total width is capital T. So if this is the case, the impulse response, and what to know about this ZOH? It would hold the last sample value for entire sampling interval. So what is the value of this? This would hold it. So this is used in the reconstruction process. This filter is used to a filter, or you can call this zero order hold, whose impulse response is this. So if this is the impulse response rectangular function, and what should be the Fourier domain representation or the Fourier transform? Here h of omega magnitude is 0, fs by 2 and fs, and this is the fs by 2 filter the response which is here, just need not be known here. So sinc function which would have the fs here, 2 fs here, and minus fs and 2 fs. So the rectangular function whose Fourier transform is sinc function. So this won't be of much use to learn what is the ZOH, and this is the impulse response of it could help us to visualize the reconstruction process. So let's see the response here. So the h of omega is a sinc function, that's a representation simply. So if we take the impulse, that is a signal impulses, suppose this is going to be here. So this is the signal, original signal x of t, and it is now sampled. So we have these samples, and we are now, after sampling, we got the spectrum. In time domain, what we do is that this is with respect to t, and this we are going to get as x of t, which is the reconstructed one. So we pass through this first impulse response rectangular function. This impulse is passed to a filter having this response. So you would get this response first. Okay, so this is the response we get. Okay, after that the second impulse is passed through that same impulse response. So it would result in, this impulse would result in a response of here, which is shown. So similarly, the third impulse would show, is when it is passed through the ZOH, it would show the response as this. Okay, so fourth one, and similarly. So what we get ultimately is a signal which is having this one. So we get, this is the signal which is reconstructed. This is closer to the value of the signal x of t. Okay, so the reconstructed signal is x hat of t. So the thing to be understand is we use the ZOH whose impulse response is a rectangular function. So when we pass an impulse to this ZOH, it would respond with the rectangular function. So that's what it is doing. So when we pass the sampled sequences, and that sample sequence response is this, which during the reconstruction. So that's how we get the sample which is hold for an entire period of time. So the same value is held here. Okay, so this is how the red portion is giving the signal which is reconstructed. So this is through the interpolation, or the zero order hold, ZOH, also called the interpolator, which is doing the interpolation between the two samples. Okay, so that's how these two samples are connected. Okay, so that's what is made. So this is one process of reconstruction using the ZOH. So similarly, the other, we can use the reverse way. This h of t is going to be sinc function. So in the previous case, in the ZOH, we had the impulse response as rectangular function. Supposing the h of t is sinc function, in that you have h of t is going to be this, and its Fourier transform would be rectangular function. If this is sinc and this is going to be h of omega, that is not necessary for the discussion, but still this h of t. So now impulse is passed, this filter has an impulse response this. So if an impulse is given to this filter, and its response would be sinc. In the previous case, when the impulse is given, this response is a rectangular function. So now having this filter, which is the TFS by 2 filter, whose h of omega is this. So anyway, this is not needed for the discussion. So now when you pass this h of x of t in h of t minus nt, so we get the reconstructed sequence as this. We'll get back here. So for this impulse, suppose the signal which we got, and it is passed through the function which is having the impulse response. You can see the first it would respond like this one. This is the impulse response we get for this particular impulse. If it is a sinc function as the impulse response, for this impulse again we get this sequence here, the second one, and for this impulse, that one again we get this. Okay, so the next one we get the sinc function as this. So similarly for the every impulse you would get a sinc function. So like every impulse we got a rectangular function in the previous case, we get a sinc function. It is much smoother than the previous one. So this is a filter whose response is this is ideal rectangular function. That's a low pass filter here. So this is a low pass filter. This interpolator can be now visualize the reconstructed signal which we got here. So this x of t is the reconstruction signal, which is always represented with a cap or hat here. X hat of t is the reconstructed signal. So this is the one which is in the brown color is the signal which is going to be a reconstructed. This is much smoother here compared to the previous one. So each sinc function is the resultant of the impulse which each impulse which is passed through that filter. Now getting the expression of this reconstructed one is n is varying from minus infinity plus infinity, x of nt and it's the shifted impulse. Okay, so you can see the shifted impulse. So that is going to be the sinc function. The representation of h of t is a sinc function. So just a representation of how do we get the sinc function. This is a summation of all the sinc value functions getting the reconstructed signal. So these are just two ways in which that reconstruction has been done. So one is with the rectangular function as impulse response, another one a sinc function as the impulse response. Now coming to the aliasing part of the sampling, which has practically it is not band limited. The signal is not band limited. So what get the signal x of omega is not like what we had in the example minus b2 plus b. It is having minus infinity to plus infinity. If that is the signal sequence is from minus infinity to plus infinity, then the response what we have here is a signal. You have the frequency of all of them, and the sequence x of omega which is having the spectrum x of omega here is from minus infinity to plus infinity. If you use this for sampling, that means if you sample this signal, okay, what it would do, this baseband is going to repeat because of the impulse which is multiplied in the time domain, and you get the convolution process. You get the repetition of this baseband due to sampling. So you get one baseband here, another one here, that would be here with respect to fs. Similarly the other minus fs, and it would continue with 2fs and minus 2fs as well. So if we don't follow that Shannon sampling theorem we have seen in the example, so this two overlaps. This portion is from the next fs band spectrum. Here is the baseband value. So this high frequency component here appearing as a low frequency component, and these things here you can see there is a overlap between these two components here. So the aliasing is like the high frequency component appearing as low frequency component. Fs by 2 is this, we use the filter to remove it, the higher frequency components. Then fs by 2 plus f1 this portion, and fs by 2 minus f1 this portion, this would show as this. So that's called the aliasing. This is a sampled sequence spectrum x delta of omega. If we don't follow the sampling theorem, that is one thing which causes aliasing, but this case is due to not band limiting. The sequence is not band limited, so this is going between minus infinity to plus infinity, and similarly this spectrum with respect to fs is going from minus infinity to plus infinity. So here also it's happening from minus infinity to plus infinity. So aliasing is not only due to the case of where you don't follow the sampling theorem, but it is due to not band limited sequence. So the band limit signal is not band limited, then if you do with some sampling frequency, and it would cause this aliasing. So this is the first case So it should be band limited. Okay, so if you reconstruct it, this is the original signal. So you are losing some information in it. The spectrum reconstructed signal, it will have the spectrum this way because of the case of overlapping. You would lose the information here. The reconstructed signal spectrum is this. So what we get is, due to that, if it is not band limited, loss of tail, that is this portion, and we have the reappearance here in this, the high frequency component, Fs component, would also be representing here. So that it is inverted and folded here and in the spectrum. So we need to use the anti-aliasing filter. First, band limited, that is a filtered sequence. So if you have the band of frequencies more than this, so use a anti-aliasing filter and filter it this way, and then follow the Shannon sampling theorem, because when you band limit it, you would know what is B and follow this to B at least, so that this would have the spectrum of the reconstructed signal, where if we use the low pass filter, exactly you can recover this portion from this. There is no aliasing in this case. Okay. So if you don't follow, then you would have this, the original signal. And so there are two things to be noted. This x of omega is distorted because of tail of beyond that Fs by 2 is lost, that is one thing. And then the results of it has a signal content. Okay, so the high frequency content which is there is lost, and the high frequency content, because of the overlapping, it appears as a low frequency content. So that is also a distortion. So that below Fs by 2, the Fs by 2 is the called the folding frequency, or the spectral folding or aliasing. So Fs by 2 plus F1 is showing up as a Fs by 2 minus F1. F1 is the one which is the tail portion of it, what we are saying here. So this causes distortion in the low frequency signal content. Actually the band has some frequencies. Because of this F1 showing it minus F1, this is having the distortion. The low frequency content has the distortion. So we need to know that it is the two things in the aliasing can occur. One is not following the Shannon sampling theorem, as we had seen in the previous example, the sinc function, and that is not following the undersampling case. Or if the signal is not band limited in practical cases, if you don't use the anti-aliasing filter, then that would also cause an aliasing. So because of that, we need to band limit the signal using the anti-aliasing filter, so that you know the band frequency and we can easily choose the Nyquist sampling as well. So the high frequency component appears as the low frequency component is nothing but this aliasing here with respect to the folding frequency. So the anti-aliasing filter x of t, if we have, pass it through a low pass filter, anti-aliasing filter, band limited, this is a filtered sequence, and then pass it through the impulse sampler, that is the impulse modulation what we have done. You get the sampled sequence and its spectrum. So after this process, for reconstruction, use a low pass filter which can limit only the baseband and remove all other frequencies with the replicas due to appearing in the spectrum due to the sampling. So anti-aliasing filter always precede the sampling. So if you don't know the band of the signal what you have, first use the anti-aliasing filter and filter it and then sample it. So there are this aliasing can be thought of as a multiple folding case. So it is not only the magnitude and phase also needs to be known in this case. So if x of t is a real signal whose spectrum is x of omega, what is that the folding with respect to Fs by 2 occurring, and the phase change in the spectrum needs to be known. So supposing we take the x delta of omega, which is a repeated spectrum here, 0 to plus infinity and minus infinity, both the directions, this would continue the repeated portion. So if you take, this is the base one, you can see 1 by t x del of omega, and this is with respect to the next one, 1 by t x del of omega minus omega naught, and this is minus 2 omega naught, similarly omega plus omega naught, and so on. So this is S we had taken omega s, and what are the frequencies? This is centered at Fs and this is centered at 2 Fs and minus Fs, and similarly minus 2 Fs, and it continues. So we can think of this, the spectrum which is over here, and there is a overlap from here, and from this next one and so on, we instead of looking at fs this portion and the fs minus fs this portion, so we can have within the fs by 2 itself how are these frequencies would be. That is one for fold 1 is 1, and next is fold 2, fold 3, fold 4, fold 5, and so on. It's like a paper which is folded and wrapped. So we'll visualize it in the future classes like that. So the fold 1 is this, and then comes the fold 2, which is due to the frequency. This is 0 to fs by 2. If you visualize it, the fs and 2 fs component. This is from fs component, and again this would be fs plus 1 by 2, and this is from 2 fs component. So what we say is, in the phase response, it's not only the magnitude response, the phase response should have the phase reversal because of the sign change, which this is coming from this spectrum and this is coming from this spectrum. So this would be cut off due to the filtering. So we get the phase changes. We look at the phase reversals, what is happening in the fold due to the aliasing. So aliasing frequency is concern is 1, and when we change when we find out what is the aliased frequency due to sampling, when we find it out, we should also look into what is the phase of that signal, the signal which is sampled when aliasing occurs. What is the aliased frequency? That's not only the problem, and what is the phase change, where the sign change in phase needs to be noted in the cosine and sinusoidal signals is the concern. So that we would discuss in the future lectures, or how do we introduce the phase with the example. So there is phase reversal needs to be introduced in the fold 2, fold 4, and so on. That because x of omega is x of omega in the positive frequencies. If it is negative, the angle is minus negative, which is minus x of omega. So this phase reversal needs to be taken care in fold 2 and fold 4 cases of the previous example. So it's, if we consider this aliasing as a multiple folding, it's not only the frequency which is aliased, and what about the phase happening in those signals. So to get it, 1D, this lecture is about the 1D sampling. So we are discussing that about what is the 1D sampling, what is the impulse modulation, where multiplication in the time domain, it's going to be a convolution of the spectrums. So when we get the convolved spectrum, that is the resultant spectrum of the convolved sequence, in this it is equivalent to the impulse response, which is impulse response of the signal what we got it. So the spectrum is now having the aliasing or not. So if you follow the Shannon sampling theorem, then there is no concept of aliasing arises in the resultant spectrum. If we don't follow the Shannon sampling theorem during the sampling, then there will be aliasing. This is not only the case that aliasing occurs. If the signal is not band limited and you sample it somehow, and that would also cause aliasing. So it is a mandate to the real time signal should be band limited using an anti-aliasing filter, and then sample it. So sampling, during sampling follow the Nyquist sampling theorem. So once getting the sampled sequence, perform the operations or whatever, can we do the reconstruction x of t back. So if you follow the Nyquist sampling theorem, yes, it can be taken back to x of t through this reconstruction process is what we had. If the impulse response of a filter which has the rectangular function, the impulse response of a filter which has a sinc function. So then the two cases we saw to get the signal back, the reconstruction signal. So ZOH under the filter with fs by 2. So the smoother one is, the later one is the smoother one. So you can get the reconstruction possible. So the whole reconstruction is possible only if you follow the sampling theorem. So if again the aliasing can be occurring in the signal sampled sequences due to two reasons what we had stated earlier. Thank you.